Hello everyone. So in this series of videos, we're going to cover the material of Calculus 2. This is the front page of our textbook that we're using. This is the same textbook that you have used in Calc 1. Now in Calc 1, you stopped at chapter 5. In Calc 2, we're going to continue from chapter 6. From chapter 6, we're going to cover 4 sections: 6.2, 6.3, 6.4, and 6.6. Regarding section 6.1, I need you please to go through this section as a self-study. This is really important. You just review some of the important formulas and technique you have learned in Calc 1. So this is a self-study section. You need just to go through all of the important integration formulas, and one of the very important technique I need you to go through is the substitution method for integration. What we'll be covering today is section 6.2, which is very important technique, which we call the integration by parts. Integration by parts. Now, from where did we get this rule? What's the rule? How can we use it? And when to use it? Now, firstly, I added for you some of the rules that you may need during this section. Okay, so these are some of the very important rules of integration. Now, from where did we get this integration by parts rule? Remember just that the integration and differentiation, they are super related to each other. And for each differentiation rule you have learned before, we can easily get another corresponding integration rule. So if I think about the product rule, okay, remember the product rule says what? If you have two functions, okay, let's say I have f of x times g of x, and I need to find their derivative, okay, the derivative of their multiplication. The product rule says what? That this is the derivative of the first times the second, plus you keep the first as is, the derivative of the second. Now let's say I need to cancel out this derivative. How can I cancel out the derivative? I'll use the integration. So if I take the integration for this equation, f of x, g of x prime, for sure it's with respect to x, equals, you see, I'll take the integration for term by term, equals f prime of x, g of x dx, plus the integration of f of x, g prime of x dx. So what I've done so far, I'm trying just to show you what's the integration by parts. How did we derive the rule for integration by parts? So it's basically, or originally, coming from the product rule. So if I have two functions, the derivative of their multiplication, this is the product rule. If I find the integration for the whole equation, notice for this first one, the first term, the integration of the derivative, they're going to cancel each other, so you get the original function back here, f of x times g of x, equals, I'll keep these two as is. Integration f of x. Can I here just cancel the derivative? No, because there's two functions. One of them derivative, one of them is just only the function itself. So I don't want to use the integration to cancel this derivative. I can do this partially. It's multiplication, not addition. So now what I'm going to do next, okay, I did the integration. I'll come to this term, okay, this one. I need to solve this equation for this term, or I'll let this term to be the subject of the equation. So I'll come here, I'll need this, the subject for the equation. So I'll make it the integration of f of x, g prime of x dx equals f of x, g of x. If I need to solve for this, I have this guy here. I'll send it to the other side and I'll switch the sign. So this is negative f prime of x, g of x dx. And this is the integration by parts rule. This is the integration by parts rule. Okay, now if we look carefully at this integration by parts, what do we have? Usually this is the part that we'll see. So I have a function which I can consider as f of x, and another function which I can think about it as g prime of x. Now, if I need just to use the formula, what are the components that I have here? I have f of x, okay, it's already given. I need g of x, which is the integration for g prime, okay. And I have f prime, which is the derivative of f, easy task. G of x is already, we used it here. It's again the integration for g prime. Now there's another nicer way to write this rule, just to make it easier, faster, rather than writing all of the functions. So let's say that we have the two original functions that we start with. We write them as using this notation. So let's say that u is f of x and v is g of x. So the formula will look something like this. So the integration of u dv equals u times v minus the integration of v du. Now the rule is here, easy, you can easily follow. The only part that you need to be careful with is your choice, okay? What's your choice? How can you decide which one to use as u and which one to use as dv? So a good choice will make our life much easier in solving these questions. If you have a poor choice, maybe you'll have a long path, many steps to solve the question if you can solve it. So basically, it's very important to have a good choice here for u and dv. Now let's just try one question and see what can we do there. Okay, let's just see practicing this rule and see how can we decide which one is u, which one is dv. Now the first example here, this is example 2.1, which is very famous type of questions that we use always, integration by parts. This question usually has a combination of trig function like sine, cosine, and algebraic expression, x squared, x power 3. For this type of questions, we always use the integration by parts. But remember, in the exam or once you have any problem you need to solve, it will not be within the section of integration by parts. So you need to decide which method to use. So by the end of this chapter, you're going to learn different techniques, different cases. So this is how I want you to think about any question. Look carefully at the question. The first method I want you to think about is integration rules. Can I use the integration rules directly here? Is there any rule for x times sine of x? No. The second technique I want you always to think about is the substitution method. I have two functions here. Is one of them the derivative or part of the derivative of the other one? No. Now the third technique you have to think about is integration by parts. So this is the way. Rules, integration rules, substitution method, then I move to integration by parts. Okay, this question is a famous case of integration by parts. Now, how can I split these two functions? Notice that I have two functions here. I have x and I have sine of x. Now, which should be which? Now, the rule is what? Again, I'll write the rule here in front of you. So this is the integration by parts rule. U dv equals u times v minus the integration, switch this, v du. Okay, now let's say I did this choice. So I'll let u be equals to x and dv be equals to the remaining part, sine of x dx. Now remember, what do we need? We need du. How do I get du? The derivative of u. So du is equal to dx. And from dv, how do I get v? It's the integration of dv. So it's the integration of sine of x dx, which we know it's equals to what? Negative cosine of x. Okay, no need to worry about the constant here. Now, the rule says what? The integration, this is our original question, x sine of x dx equals to, now how do I write it? I come here, I'll multiply u times v, remember this order, it's easy to recall, u times v minus the integration of these two. Now u times v, what's u times v here? It's x times negative cosine, so it's negative x cosine of x minus, remember always with negative you need to be careful. I have negative in the rule and there's already another negative here, so negative negative is positive again. What do I have here? I have the integration of cosine of x dx. The integration of cosine of x dx. Now, this first term I don't have to worry about. It should be always ready, nothing to do further for this one. For the second one, this is where I need to again do the integration. Now, basically, if you have done the correct choice, always this new integration should be easier than the original question or maximum same level of difficulty. It shouldn't be harder. Now, looking at this one, can I easily find this integration? Yes, this is one of the rules of integration that we know. What's the integration of cosine of x dx? We know it's equals to sine of x. So, okay, so this is equals to, first part, nothing, just carry it with you, plus the integration of cosine is sine of x. Remember, this is indefinite integral, so I have to add the constant term plus c. And this is our final result. Easy, simple. Okay, now, just to show you how important is your decision at the beginning. So this is for me, just like the most important step is this one, your first step. Okay, which one you decide as u or dv. Now, let's say, okay, for the same example, I had the different choice. I switched my choices. So for the same question, okay, let's say for this question, I let u, remember first time u was x. Now I'll do the opposite. I'll let x be dv and sine x be u and see what will happen here. So let's say that let u be equals to sine of x and dv equals the remaining part x dx. Du will be equals, the derivative of u is cosine of x, integration of v is x, so the integration is half x squared. Okay, now let's follow the rule. The original question, x sine of x dx equals to, remember what do we need to do? This multiplication minus the integration of this one. Okay, so this is equals to u times v. This is no need to worry about always. It should be something ready. Minus, is there any other negative here? No. So it's minus the integration of half x squared cosine of x dx. Okay, now look at this part. Remember, this is the one that we need to worry about again, because this one is ready. This one we need to find the integration again. Compare it to the original question. We started with one trig function, a linear function, just x to the power of 1. We end up with, still it's a trig function, but x to the power of 2. So what I have done here, I make the question more complicated. Okay, can I continue from here? Yes, you'll know later on we'll cover this part. You need just to solve this by using integration by parts twice. So it's like more work to be done. I need to solve this question by integration by parts twice. So a bad choice or a poor choice will make our question like more difficult, more steps, sometimes you can't solve it. Sometimes you end up with an integration that you can't find the integration. Here, okay, I can, but it needs really a lot of steps extra. So a good choice is always very important. Now, okay, teacher, you said that a good choice is important. How can I decide then? Is it like trial and error? Do I have that extra time during exam to keep trying? No. There's a nice guideline. We can always use it. It's like works most of the time. This guideline, we call it the LIATE guideline. We call it the LIATE. Now, these are some of the famous functions that we see in our questions. And according to this guideline, it helps us just to decide which one to use as u. What should be your assumption to be as u? Then for sure, the remaining part will act as dv. Now, LIATE, these letters stands for what? L is a logarithmic function if you have len, log. I for inverse trig function if you have sine inverse, cosine inverse, tan inverse. A stands for algebraic function, anything like x squared, 2x, radical x, any algebraic relation. T stands for trig function, so if you have sine, cosine, tan. E finally stands for the exponential function, so if you have like e to the power of x, 3 to the power of 2x, any exponential function. Now, I always look at my question. We know that it has two different functions. Whatever comes first, okay, in this order, in LIATE, whatever comes first, I assume it to be u. So let's try to apply the LIATE in our previous example, okay, just to see if it works or not. I'll go back to this question, okay, the one that we already covered. So what did we have here? We have the integration of x, sine of x, dx. So basically, if you look carefully at this question, and you have x, which is algebraic expression, and you have the sine, which is trig function. Now, the LIATE says what? LIATE. So look here. A and T, I have these two letters, A and T. I have the A and I have the T. Which one comes first in the word LIATE? I mean the order within the word LIATE. The letter A comes first, right? In LIATE, the letter A comes first, which means this is the one that I will let to be u. So I'll let u be equals to x. Okay, so whatever comes first, we'll assume it to be u. This is really a useful guideline you can use most of the time. Now, we covered the basic information about the integration by parts. We know now how did we get the rule, when to use it, the guideline to help us to decide which one is u, which one is dv. Now what we'll be doing from now till the end of this section, we'll be solving more problems, more examples with different level of difficulties, different cases, but the basic knowledge is the same. Now, we'll move to the next question, which is a very famous one. It's the integration for len of x dx. Now, we know the derivative for len of x. You already covered that in Calc 1. So the derivative of len of x is 1 over x. Now, what's the integration for len of x? Did we take any rule so far for the integration of len of x? No. Now, how can we find this integration? So do we know any rules? No. Can I use substitution method? No. Okay, so let's try to use integration by parts. Now, this function, maybe it looks initially like you have one function only, but still you have dx. So I can split it into two parts. This one, this one. Okay, so this one dx, you can think about it as 1 dx. Okay, so dx is basically 1 dx. Now, what are the two functions available here? What do we have? So if you look carefully, I have len of x, which is L, logarithmic function, and I have 1 dx, which is algebraic, right? It's one only. Now, if I think about our rule, which is the LIATE, which I need you always to think about. So I have here len of x, and I have d of x. So let's think about the LIATE. We have the LIATE. The two letters available here for me are L and A. This is A, and I have L, the logarithmic function. Now, which one comes first in the word LIATE? L, the logarithmic function. So that means L should be used as U. So now I'll say what? Let U be equals to len of x. So basically dv will be what? Dx. Remember, first one, I need to find its derivative, du. So the derivative for len of x is equals to 1 of x dx. The integration for v is equals to what? X. Now the rule says what? I need the multiplication of these two minus the integration of these two. Okay, so the question itself, the integration of len of x dx equals to u times v, so it's x len of x, minus, is there any other negative? No, the integration of x times 1 over x dx. Okay, perfect. Now this is equals to what? X len of x, the first term is as it is. Here you have x times 1 over x, which can be easily cancelled out, x with 1. So this is equals to the integration of 1 dx. And is this one easy to find? Yes, for sure. So this is equals x len of x minus x plus c. And this one, I need you to learn it now by heart. This is the rule for the integration of len of x. So now anytime we need the integration for len of x, it's equals to what? X len of x minus x plus c. Okay, the integration for len of x equals x len of x minus x. So now what I want from you, just you add this one to the integration rules that you have learned before. Okay, very important. So we had a good choice here. It makes everything easy. We were able to find the integration. Okay, let's see another case. So this case is the integral with a single term. So the other function, we use it as dx. Okay, so don't see this question as only one function. How can I make it by parts? Still, you can see it as two parts. We always can consider dx as one part. Now, let's try another question. This one. So what do we have in here? I have x squared sine of x. This case I told you about at the beginning. The case of one trig function, sine or cosine, with a polynomial, power x to power to the power 1, power 2, power 3, or 4, any power function. Now, in this case, I need first to use the LIATE and see what will happen with us. Now, for the LIATE, what do I have? X squared is algebraic expression, and sine is t. So looking again at the LIATE, for the LIATE, which one comes first? A comes first. I have A and T here involves. So A comes first, which means x squared should act as u. Okay, so what I'm going to do, I'll say let u be equals to x squared. So dv will be the remaining part, which is sine of x dx. For u, I need its derivative. Du equals, you drop the power down, minus 1 dx. dv, find its integration. The integration of sine, we know that it's negative cosine of x. Now, to apply the rule for this question, we need this multiplication minus the integration of these two. I always prefer to call the original question as I. It's really helpful, especially with these cases. You can do it for any question. You can always call your original question as I, just like annotation. So now I is equal to what? I need u times v, right? So this is u times v. So it's negative x squared cosine of x minus, I want you always to check. Once you have negative, look at this line. Is there any other negative? Yes. So this negative will turn into positive. The integration of these two. So what do I have? 2x cosine of x dx. Okay, perfect. Now look at this one. What do I have here? Now compare it to the original one. As I told you before, always when we use the integration by parts, we need this integral to be either very simple, we can always solve it directly, or it should be at least easier than the original one. So we started with x to the power of 2 with trig function. We end up with x to the power of 1 with trig function. So it's easier, simpler than the original one. Now, what can I do with this new function? It's again a question that can be done by integration by parts. That's why they call this case the repeated integration by parts. So here I need, if the power is 2, always it looks like the power. How many times do you need to repeat the integration? If power 1, like the previous question, we did it once only. If the a is to the power of 2, so I need to do it twice. If it's power 3, I need to do it 3 times. And the same thing goes on with any power. Now, for this one, I need again to do it by integration by parts. So I need to do the same decision again, but fast this time. So I have 2x, which acts as a. I have cosine as t. So looking at LIATE, a should be u. So let's do it here at the margin of this page, here at the side. So u should be equals to 2x. dv is cosine x dx. Now du will be equals to what? 2 dx. And v is equal, the integration of cosine is sine of x. Okay, so this is the integration, the second one. We can just fill it here, okay, this part. And this is equals to, so I'll go back, this is I equals, remember always, when you continue your solving, you need to carry over any term from the previous step. So it's negative x squared cosine x plus. Now this term is 2 terms now. I need to use it as u times v. So this is 2x sine of x minus, again, as usual. Is there any other negative? No. So this is the integration of 2 sine x dx. Now look at this new integration, this one. Is it easy? Can we find it easily? Yes, clearly. You see, just with the difficulty, just going like less. Power 2, power 1, now constant term. Now this one, we can easily find its integration. Perfect. So now finally, I can say that I is equal to, again, remember to carry over anything in the previous step. So 2x sine of x minus, now we stop here. What's the integration of sine of x? The integration of sine of x. We know the integration is equal to negative cosine, okay? Negative cosine. And there's negative outside, so now this is positive, okay? 2 cosine x, and don't forget the constant term plus c. So this is the final result. It's equals negative x squared cosine of x plus 2x sine of x plus 2 cosine x plus c. So this is a case where we need to do repeated integration. Integration by parts twice. So we did it the first time. We noticed this new integral. It's just like the original one, but it's a bit easier. So instead of power 2, we have power 1 here only. So we repeat the same process again, but please always be careful about this sign. If it's positive, okay, you're on the safe side, no issue. But if it's negative, use brackets. Always, anytime you have negative sign, use brackets, so you don't forget to distribute the negative over these two terms. Here it's positive, so we're okay. So the integration by parts, I could do it here on the side. It's just, I'll split this into two parts. This one is easy to integral. Just we find its integration and then that's it. We're done. Okay. So this is another case. Still, we're doing the same technique, but it's just like a bit needs more work. Okay. So it's repeated integration by parts. We need to do it twice. Let's say if x to the power of 3, I have to do it 3 times. X to the power of 4, I have to do it 4 times. So that's it. So power 2 is easy. Okay, I have to do it twice and I'm done. Now, let's see what do we have next. Next, we'll have another question where we need to repeat the integration by parts, but with a twist. Okay, so this coming question will be just repeated integration by parts with a twist. So let's see what will be this twist. Now, this function has what? Exponential function and trig function. Now look at this function again, at this question. Can I use the rules directly? No. Can I use substitution? No. Sine, derivative, cosine, exponential, still exponential, so nothing can be cancelled out. So no substitution. I need to think about integration by parts. Now, what are the two components that I'm having here? I have the exponential as e, and I have the sine function as t. The sine function as t. Now think about the LIATE again. I always keep it in front of me so I can decide. So what do we have? We have e and we have t. So which one comes first? Clearly t comes first. So the t should be our u. Remember at the beginning I told you that this guideline works most of the time. For this question, I can easily switch my choice and it will still be the same difficulty level. I can switch them. But why not? Let's follow the guideline, easier for the future. But if you switch the choice here, it's still okay. It will be the same difficulty level. But I'll follow the LIATE. Now, so u will be equals to what? We said u is the t. So sine. So sine of x is u. dv will be equals to e to the power of 2x dx. Okay. Now, for u, I need to find du, which is the derivative of sine, cosine x dx. For dv, I need to find the integration. Remember, please, when you do the integration on differentiation, remember to use the chain rule. So here, the integration, I need to divide by the power of this function. So it's equals to half e to the power of 2x. Okay, don't forget the derivative of the power. When you do integration, you have to divide by this derivative. If it's differentiation, you multiply. Okay, so if I need to do, let's say, the derivative of e to the power of 2x, it should be 2e to the power of 2x. If it's integration, you notice I divide by 2. This is a common mistake that I see with many students. Okay, now we'll follow our usual steps. This is multiplication minus this integration. Again, I always prefer to call the original question, use the notation of I. So I is equal to, let's see what do we get. U times V, so this one always we no need to worry about. E to the power of 2x sine of x, negative, again, don't forget my advice. Negative, is there any other negative? No, so it's only one negative. The integration of half, remember half is a constant, I can just take it out of the integration just to make it easier. E to the power of 2x cosine of x dx. Now this integration, this one. If you look at this integration, this is again looks like the original one, same difficulty level, still exponential, still trig function. Now, what do I need to use just for the assumption? Please here, just if you do use LIATE at the first part, use LIATE here also. So for this one, let's do the integration by parts. So this is again E, this is T comes first, so I'll do the integration by parts here on the side. So U should be same as before, cosine of x, dv should be e to the power of 2x dx. The derivative of u is du, so this is equals to, the derivative of cosine is equals to what? So the derivative of cosine is negative sine of x dx. The integration here will be again half e to the power of 2x. And I'll follow the integration by parts. Okay, let's do it here. So now what do we have? I is equal to, again, don't forget to carry over any terms you had from before. Half e to the power of 2x sine of x. Notice I told you before, if there's a negative, be careful. Negative half, and I'll open brackets, so I don't forget to distribute the negative half later on. Now this integration, this is the one by parts. U times v, okay, so this is half e to the power of 2x cosine of x minus, again, is there any other negative? Yes, there's one here. And I have negative originally in the rule, so negative is positive again. The integration of, I keep the half outside as usual. So half the integration of e to the power of 2x sine x dx. Now I need you to concentrate here, okay? Let's go back from the beginning. The question has exponential and trig function. We've used the integration by parts one time. We end up with a question with similar difficulty, let's say, same level of difficulty. We decided to use integration by parts again. I did it here. So this is the integration by parts, and I told you again, be careful if you have any negative or constant, so you use brackets, so don't forget to distribute negative half over these two terms. Now here's the twist. Now I look at this one. This one, if I keep doing the integration by parts, it will be like endless. I keep getting the same thing. It's exponential sine, exponential cosine. So the time where I can stop when I get something similar to the original function. So look at the original equation, sorry. The I is equals to what? E to the power of 2x sine x. I end up with the same one. That's why I prefer always to use the original equation as I. Now notice this highlighted part is again our original I. This is I. This is I. It's exactly the original question. So now what can I do next? I'll replace this with I. Remember, our target is to evaluate I. And I'll solve this equation for I. There's nothing else I need to do. This is already ready, no integration. This is ready, no integration. I have only this part, which needs to be written as I, and then I'll solve the equation for I. Okay, now see what can we do. So we have the one integration by part, second time. Now let's simplify this one. Let's just move to another slide. Okay, I'll continue from where we stopped in the previous slide, okay, from this step. So what I had here was I equals to half e to the power of 2x sine of x minus half, I've used the brackets before, half e to the power of 2x cosine of x plus half, remember this one, I replace it with I. So this is half I. I close the bracket. Now what's the next step? What you need to do? Just only basic algebra, simplify. I need you only to solve for I. Remember, I is what we need to evaluate from the original question. Okay, do some basic algebra. I'll distribute this here. So I is equal to half e to the power of 2x sine x minus half times half quarter e to the power of 2x cosine x. Remember, negative times positive, negative 1 over 4i. Now I need to do what? Solve for I. So I need to move this guy here to the other side, or you just add 1 over 4i to both sides. So I plus 1 over 4i equals to, what do I have here? Half e to the power of 2x sine x minus 1 over 4 e to the power of 2x cosine of x. Now 1 plus 1 over 4i is equals to what? 5 over 4i. Please do the fractions correctly. If you're unsure, just use your calculator, but don't do it wrong, okay? Now 5 over 4i equals to this. Now the last step, I'm showing you all the steps in detail, so you don't do any of the common mistakes in simplifying in the next question. Now I need to solve for I. The only part here annoying us is just 5 over 4. How can I get rid of this 5 over 4? You multiply the whole equation by the reciprocal, which is 4 over 5. Or you divide by 5 over 4, same thing. So now the question is, or the final result is I equals, if you multiply by 4 over 5, so this is 2 over 5 e to the power of 2x sine of x minus, cancel 4 with 4, 1 over 5 e to the power of 2x cosine of x, and don't forget to add the constant at the end. Okay, no need to worry about the constant in each step. At the end, you just add your constant. So hence, clearly we have I as this part. This is the final answer. And this is a case, a very important one. Okay, so this is the case where we need to do integration by parts with a twist. And basically you see this case usually in any question which looks like exponential, okay, exponential with trig function, basically sine and cosine. So the case of ET is where we need to do repeated integration by parts with a twist. Because else you'll keep doing the integration non-stop, okay? You will never stop. So when do I know when I need to stop? When I get something similar to the original question, the original one, I. Notice here the constant cause no issues for us. We can always take it out, and this is still I, okay? So this is now half I. So now what did we see so far? We saw the cases of classic integration by parts, normal one as question 2.1. And 2.2, we did the ln of x, which is a famous one. I need you to consider as a new rule. We saw a case where we need to do the integration by parts, this one, where we need to do it twice. And this case, basically, usually you see it when you have any power function with sine and cosine. So I need to do it repeated integration by parts. How many times do we need to repeat? It depends on the power function. Power 2, you do it twice. Power 1, you do it one time. And the case with a twist, when you have ET, okay, any trig function, sine, cosine, and exponential function, then this one should be a repeated integration by parts with a twist. And this is an important one. An easy hint I give you just is to do it by letting the original question to be I. So it will make it much easier to follow, okay? So it's easier to write it as I, as I've done here. So you'll meet I again in the same equation, solve for I like normal algebra, and then you can easily finish that question, okay? Okay, now let's see what do we have next. Next, I tried just to add another nice question. I'm trying what I'm doing here with you. I'm trying to go a bit with a difficulty level, okay, like step by step. With each example, I'm trying to introduce new idea maybe, or make the question a bit harder, or يعني needs more steps or difficulty level a bit harder. Now see this question. What do we have in this example? Okay, this one. Okay. We have x tan inverse of x. Fine. Okay. Again, I always recommend using the guideline. What do I have? X stands for A. It's an algebraic expression. Tan inverse is the inverse function, so it's I. So again, think about the LIATE. It's good to always to write it in front of you so you see. I have A and I. These two. I have A and I. So which one I need to use, or which one came first here? I, the inverse trigonometric function. So this I should be used as U. Okay, fine. So I'll let U be equals to tan inverse, not X. You see, maybe if you just solve it by yourself without thinking about the LIATE, maybe many students, they tend to choose X as U. So U is tan inverse of X, dV, I'll use X dx. Okay, that's good. Now, what's the derivative for U, du? This is something you need to know from Calc 1. The derivative of tan inverse is 1 over 1 plus x squared dx. And what's the integration for V? This is the easy one, half x squared. Okay, now one more time. I like to call my original question always as I. Now I'll multiply these two minus the derivative of these two. Okay, good. So now what do I have? I equals U times V. Always no need to worry about this part. So this is half x squared tan inverse x minus, one more time, check if you have any other negative. No other negative. So I have half x squared times 1 over 1 plus x squared. I'll keep the half outside. And if you multiply these two, notice here you have x squared times 1 over 1 plus x squared. So these are like multiplying fractions. So I'll multiply the numerator with numerator, denominator with denominator. So this is basically equals x squared over 1 plus x squared dx. Okay, good. Now, looking at this question, it's a bit different scenario, this one. I have it as a rational function. Remember, if you divide polynomial by another polynomial, we call it rational function. So this is, I need to do an integration for rational function. Okay, how can I do that? Now for this specific question, notice that the degree is the same. Numerator and denominator, they have the same degree. So I need to think about maybe using a long division or synthetic division. Here in this case, I can use only long division to make it like, I'll divide them just to make it a bit easier. Let's try the long division. Long division. How can I do the long division? I'll divide numerator divided by the denominator. Remember always to write the denominator as in decreasing order. Okay, so I have x squared divided by x squared plus 1. That's fine. How do I divide? Remember always in division. I'm just always try to go through any basic knowledge you know from before. I always start with the leaders together, leading terms. So x squared divided by x squared. X squared divided by x squared is 1. After you divide, you need to multiply, okay? And don't forget to use the distributive property. So 1 times x squared is x squared. 1 times 1 is plus 1. Some students, they prefer to use the 0 terms here. So they write plus 0x plus 0. If you like to do that, it's up to you. If not, you can easily do it this way. So this is x squared plus 1. Now here you multiply, here you subtract. So if I need to subtract these two, so x squared minus x squared, 0. Here, let's say that we have plus 0. 0 minus 1, it's negative 1. And this is the remainder. Now what I need you to, this is a recall, something really important. You took it before in the school. This is the division algorithm. So if you're dividing two functions like p of x divided by d of x, d is the divisor. Usually we get what? We get the quotient plus we write the remainder over the divisor. Okay, so this is what we call the division algorithm. If I need to write it as division, notice that I write it as what? I'm dividing p. Let's do it here on the side. So I'm dividing p of x divided by d of x, the divisor. This is the quotient, what I got here. And then after I do all the process, what's left over down is the remainder. Okay, so this is important way just always to remind, I want you to remember this division algorithm. Okay, so now how do I write the final result here? On top, I will write what? X squared over 1 plus x squared equals, the quotient is 1 plus remainder over divisor, which is negative 1 over 1 plus x squared. Okay, so this is the result I have. Now let's erase the algorithm, which I think by now you know it now. So see, what do we have? Now in this integration, this is what I have as the division. Just write it a bit here to the side. So I have x squared over 1 plus x squared equals quotient is 1 minus remainder plus the remainder, which is negative 1 over 1 plus x squared. Now this is the function we have here. Now the operation here is subtraction. Can I distribute the integration over subtraction? Yes. So this one will be equals to what? I'll go back to the original equation. So I is equal to, just carry over this term, half x squared tan inverse x. Don't forget the minus half. As I told you before, anything with negative, you need just to use a bracket. So don't forget that you have to distribute this over anything coming. So this is these two terms, the integration of 1 dx minus the integration of 1 over 1 plus x squared dx. Okay, now look at the result here. Is it easy? The integration for 1, we know it. The integration for 1 over 1 plus x squared, we know it. It's tan inverse. So I'm almost done. So now I is equal to half x squared tan inverse of x minus half. I'll distribute the minus half while doing the integration. So this integration is x times negative half, so it's negative half x. Negative half times negative 1s, it's plus half. And this integration, we know it from the rules, it's tan inverse x. And don't forget to add the constant tan. So this is the result for this question. So this is a really nice one. This is not one of the examples in the textbook, but I like to add a case where we use the inverse of trig function. Basically, tan inverse is the one, it's repeated. You see it more often than any other inverse function. Okay. So for this case, we had a rational function. So I'm using, remember that always in Calc 2, you use the skills that you have learned in Calc 1. So this rational function is easy just to be done by using the long division. Later on, we'll learn different methods for rational functions. But for this time, it's only by using the long division. So I have easier function. I can easily continue from here. Okay. Hopefully everything is clear so far. Now what I'll be doing here next, this is the same question, the solution. I always prefer just to solve it with you like in my handwriting, and then I'll add the solution type for you in case you prefer it this way. Now notice that all the examples that we covered so far were indefinite integral. Remember that the indefinite integral without the boundary of the integration. If the integration is definite, so just easy way, nothing, doesn't need much. So what you need to do after you apply the rule, you substitute the boundary. So if it's multiplication, you replace from x equals to a to b. Same here for the integration. Remember before that you had the integration from a to b. Let's say it's f of x dx. If the integration is f of x, you need to replace from a to b. How do you do this substitution? Always you do the upper bound minus the lower one, f of a. Okay, this is what you covered in Calc 1. Okay, so I'll do the same thing. I'll do the integration, then I'll replace the upper bound minus the lower. This is how I deal if the question is definite integral. Now the only part left for us today is just to learn new fast method. Okay, we call it a tabular integration method. This method is helpful for the integration which needs multiple times of repeating the integration by parts. One of the cases that's introduced here, just if you have a power function with exponential, just as we introduced before, you can think about it that you have a with exponential function, or you have it could be also trig function like sine and cosine. So anything like power function with exponential, power function with sine or cosine, we can use this tabular integration method, which is a fast method. Now, how can we use this method? One of the examples that I'll introduce here is this one. Basically, what we have here, we have a power function and we have an exponential function, okay? For this case, basically, if I'm using the classic method, okay, the classic integration by parts, you know that we're expecting that I'll do the integration by parts 3 times, okay? I have to repeat it 3 times. Now, with the tabular integration, it will make everything much faster. How? The first step should be something the same. Remember, using the LIATE, I need to let u be equals to x to the power of 3 and dv equals to e to the power of 2x dx. Now the idea from the tabular integration, they do what? They have the question like into 2 columns, okay? The first one, we keep finding its derivative. For u, remember, how do we do it usually? We start with du, okay? This is the derivative. This is 3x squared. Now, you keep finding its derivative till you cancel it out. So if you do the derivative one more time, this is 6x. One extra time, this is 6. One extra time, this is 0. Now we stop. Once you cancel the power function out, you stop. Now what to do with the other one, the dv? For this column, I'm going to do what? Integration, just like the normal way. So this is dv. Now, one time of integration, it will give me half e to the power of 2x. Now, one extra time, 1 over 4 e to the power of 2x. One more time. Now, when to stop? When I reach same number of times like the differentiation. They should be equals to each other. So this is 1 over 16 e to the power of 2x. Now, if you look at what we've got here, we started with this, our original assumption, okay? Now, what I did here, I did the differentiation 1, 2, 3, 4 times of differentiation. Same thing here. I did the integration 4 times. 1, 2, 3, 4. Now, what to do next is this. I'll come to the first one. Remember our arrow? I'll start with this. Let's use the red. So this is my first arrow, starting from U to V. And I'll do the same for the rest. Another arrow. One more. One more. So notice we have the derivative 4 times. integration 4 times, I got 4 arrows. Now, how can I write the relation? Now, these arrows means that the relation is multiplication. Regarding the sign in between, they do what? They start with the original sign with positive. So we always begin with positive, and you start alternating the sign. So we start with positive. This is a rule, always positive you start with. Then negative, positive, negative. Now, how do I write my final answer? So this is the question, the integration of x to the power of 3 e to the power of 2x dx equals to, I'll start with the first term. I multiply these two and I consider the sign to be positive. So it's half e to the power of 2x. Let's just write the power function first. So it's half x to the power of 3 e to the power of 2x. Now the second term, 3 times 1 over 4, so it's a 3 over 4, and there's negative sign, so it's negative. I'll fix the coefficient first. 3 over 4, and then x squared times e to the power of 2x. I'll move to the third term, 6 over 8, which I can simplify it basically as 3 over 4, and the sign is positive. So it's plus 3 over 4 x e to the power of 2x. And the last term is this one, 6 divided by 16, simplify into 3 over 8, and the sign is negative. Negative 3 over 8 e to the power of 2x, and lastly our constant plus c. So you see, this is the tabular integration. Really simple, fast method. We do it again, basically, if I have any power function with exponential, power function with sine or cosine. So I keep finding its derivative till I cancel it out, okay? For the dv, you keep finding its integration, same amount of, or same number of times like the derivative. Notice here, just this is a step of, I call it like a self-check that you didn't forget anything. So it should be, you have 4 arrows, 4 terms, everything is 4. I differentiate the u 4 times, integration 4 times. Okay, and don't forget about this sign. It's alternating, and always we start with positive. Fine. Now let's try another example. Okay, let's practice more. The tabular integration. Sometimes they create a table, something similar to this. It's up to you. They do here, you know, just this is u, the differentiation, integration. The last column, they do the multiplication. And then lastly, they do all of the result down. So both ways are fine. If you prefer the table or just like here, it's all the same. Now, the one additional example. Remember, this is the question that we did together as repeated integration by parts. Now we'll do the same. I'm not going to do the classic way and I repeat the integration by parts twice. I'll solve it using the tabular integration, okay? So what do I have in this case? I have x squared, which acts like a, and I have the sign as t. If we think about the LIATE, so u in this case equals x squared, and dv equals to sine of x. Remember, with the tabular integration, I'll keep finding the derivative till I cancel it out. So the first column always is the derivative. So this is 2x, 1 extra time, 2, 1 more time, 0, a stop. So I did it 3 times. Now I'll do exactly the same thing with dv, but integration. So the first column, derivative, the second one, integration. Now first time of the integration for sine, it's equals to what? Negative cosine of x. 1 extra time, the integration for negative cosine. So this is negative sine of x. 1 extra time, that the integration for negative sine of x equals to cosine of x. Now, please, I need you to be careful when there's a negative sign, because usually this is a common error. Even though it's simple, but sometimes, you know, with sine and cosine, you keep just finding sine, cosine with different signs. So what I need you to do just to make sure that you do it correctly. Always look at the function alone, then consider the sign. So if, let's say, I need to find the integration for negative cosine, I think first about only cosine. So what's the integration of cosine? It's sine. And there's already a negative sign, I carry it over. So it's negative sine. Let's say I need to do the integration for negative sine of x. So I consider only sine alone. What's the integration of sine? I know it's negative cosine. And there's negative outside, so it's cosine again, okay? Even though you feel it's really simple, basic, but it's one of the common mistakes. Now we'll do our arrows. So 3 times, 3 arrows, but remember, you start always from u. 1, 2, 3 arrows. Regarding the signs, this is positive, negative, positive. Now the final result will be equals to what? The integration, our question, x squared sine of x dx equals the first term, the multiplication of these two with positive sign. So this is negative x squared cosine of x, okay? I'll move to the second one. Negative, negative, positive, positive 2x sine of x. The last one is 2 cosine of x, and lastly plus c. Okay, that's it. You see, it's really fast. If you go back, compare your solution, this one with the method that we did before, just repeating the integration by parts twice, this is really faster. In the end, nobody will specify to you which method you use, so it's up to you, okay? You decide. So the question will not ask you use tabular or you use the classic integration by parts. In the end, it's up to you to decide which one you use. Now, as we saw in the previous 2 examples, we used the tabular integration for the famous case of power function, sine, cosine, power function, exponential. There's another case where we can use the tabular integration with something like this case. This is the same question that we introduced before. And this question was the one, if you remember, it was the one with a twist, repeated integration with a twist. Okay, so this is the one with a twist, which basically looks like you have exponential function with a t, trig function. So this is the one with a twist, the one we said that it has a twist. Now, can I use the tabular integration in this case? Yes, but again, it's with a twist. How to do this twist? You need to be careful. So please, either for this case, you learn it correctly, okay, you understand what I'm doing, or else use the classic way. Now what to do? The starting point is still the same, just I'm following the normal tabular integration. So this is t, this is the exponential function, and this is t. Now u should be what according to the LIATE, remember the LIATE that we've used before. So I have te, so I use t first. Remember, this is the case that I told you, you can switch your assumption, it's okay, but I rather just follow the LIATE. So this is dv equals the exponential function dx. Now, if I start finding the derivative, notice with sine and cosine, this is something endless. It's not gonna be cancelled out anywhere, okay? If I keep finding its derivative, it's non-stop, never ends. So if I do 1 time, let's try just to do 2 times. Sine, first derivative is cosine. 1 more time, I find the derivative, it's negative sine of x. Now, where to stop? How can I know where to stop? What I'm going to do here, remember with the case of a twist, what happened before? We kept finding the integration till we met I again. And I is basically the original equation. Here, I'll do the same thing. I'll keep finding the derivative, the integration, same number of times, till I find exactly the same original functions, the main component of the original function, which are the exponential and the sine. Okay, no need to worry about the coefficients. I do care about the function itself. So now if I do the integration here 1 time, I'll get half e to the power of 2x. Now look at these 2 new functions horizontally. Is it the same like the original function? No, I have cosine exponential. Try to do it one more time. It's 1 over 4 e to the power of 2x. Now, what do I have? I have sine and I have exponential to the power of 2x. It's exactly the original function. Okay? So, for sure, I'm not going to look at the original one from the beginning because this is already the original function. I'm looking beyond this step. This one, not the original. This one, yes, it's the original, regardless of the coefficients. Now I'll stop in this case. So I'll start with my arrows. I did it 2 times, right? So 1 arrow, 2 arrows. This is positive, this is negative, this is positive. Now I need you to concentrate with me. The twist is here. Once I stop, I'll make a horizontal arrow. And in this case, it will be like I. Okay, so in this case, I have it with the integration. So the question looks something like this. So the original equation, which is, I'll call it I as usual. So I is equal to the multiplication of these two. So it's half e to the power of 2x sine x. The other two, negative 1 over 4 e to the power of 2x cosine x. Now with this step where I need to stop, okay, this is a stop. Where I need to stop, I write it as what? Okay, negative positive, so it's negative 1 over 4. I'll keep the coefficient outside. The integration of e to the power of 2x sine of x dx. And this term is basically what? This is I. Just as what happened before with the twist. We have it as I. So now what can I do? This is I. I'll do exactly as before. I'll move this I to the other side. I'll solve for I. So I'll have I equals to, remember, if I move it to the other side, I have 5 over 4. And then I need to divide by 5 over 4, the whole equation. So this one will be equals to I equals to 2 over 5 e to the power of 2x sine of x minus 1 over 5 e to the power of 2x cosine x plus c. And I'm done. So what I've done here, just only I solve for I. So this is the step where I need to stop. You need to be careful with this step. Okay, so please, if you're trying just to use the tabular integration for this special case, the one with the twist, do it correctly. How do I do it correctly? I stop only once I see same like the original functions here. Once you stop, the last step should be with the integration. If you're worried not just to remember that you need to apply the integration at the end, remember that the last step is I. So I can write it directly as negative 1 over 4 I quickly. And that's it. You're done. So remember, the last step is your original integration. So that's it about the integration using the tabular integration method. Now, the only part maybe you'll see during solving the recommended question, you'll find something that we call the reduction formula. And again, for this reduction formula, it's not necessary for you to memorize it. It's just the idea of the reduction formula. It's a formula, like a rule you can use if you have a high powers. Instead of keep repeating the integration by parts, they give you the rule. It's not required from you. We're not going to ask you anything of these just to memorize it. But the idea in simple, just if you see the word reduction formula, you understand that this is a case where you do repeated integration. So if I have ln to the power of 3, if I do the integration by parts once, then this is to the power of 2, you repeat it, this is ln, you know how to continue. So the idea of the reduction formula, just repeating the integration by parts. They give you a formula, you can follow to check your answer, okay? But eventually what's required from you is to do what? The integration by parts, the normal one. No need to memorize any of these reduction formulas. Okay, there's many formulas. I've just added them for you, just for your knowledge, or if you need them for anything. It's helping in checking your answer if you like. but this is the idea. So they keep repeating the integration by parts to follow or to get a general formula. Okay, there's many formulas for cosine, for tan, for sine. You can check them out by yourself if you like. No need to prove it, no need to memorize it. Okay, so next time what we'll be doing here for section 6.2, next time I'll be solving some of the recommended questions, okay, from the textbook, and I'll solve some of the previous exam questions. So for today we're done. What I'm expecting from you now, just please go through all the examples that we did together. Try to resolve them. Practice, practice, practice. Remember, math is really, especially with calculus, it's really very important for you to practice by hand, okay? Don't just read the solutions. Hold your pencil. Just give any A4 paper and try to practice. And please let me know if you have any questions.